Hello viewers on YouTube. In this video tutorial, we are going to consider electric potential energy. And your first question would be, what exactly is electric potential energy? And probably, how is it different from potential energy itself? Well, potential energy is a form of mechanical energy, but it does also have different forms. Which one of it is this electric potential energy? Okay, we call it electric potential energy in order to be able to distinguish it from any other forms of potential energy. However, you might want to write this down. By definition, potential energy is the energy possessed by a body by virtue of its position. Now, we are not dealing with charge, then we have to be specific, we have to be precise, and this is the reason why we have to attach electric to the potential energy. So by definition, electric potential energy is the energy possessed by a charged body, okay, by virtue of its position. Are we together? So that clearly distinguishes it from any other forms of potential energy, either gravitational or elastic potential energy. Now let's talk more about this. Consider the two parallel plates we have right on the board. If we select two random points within the interval, let's say this is point A and this is point B. Now, if a positive charge is at point A, how can we determine the electric potential energy of this charge at point A? Notice that we can always determine the magnitude of this electric potential energy because the position of the charge actually satisfies the condition for calculating the magnitude of the electric potential energy. And the main condition is that the object must be at a certain height from the horizontal ground, or from what we are having at the horizontal is the negative plate. You can see it from the negative plate. Am I complicating? Perfect. So we can always determine the electric potential energy. So the question is, how do we determine that? To bring up a formula that can help us to determine the electric potential energy of this charge at either point A or point B. Let's take, for instance, the charge itself actually wants to move from point A to point B. Upon doing that, in that process, it's obvious that work will be done. Remember, work is said to be done whenever a force moves an object to a certain distance in the direction of the force. Yes, the charge will experience a force, typically an electric force, and that force will be in such a way that the charge will feel it with respect to this direction. Okay, the force will be attracting the charge towards the negative plate because opposite charges attract. So the positive charge will feel a force of attraction that will draw it closer and closer to the negative plate. So let that force be F. Also, remember that all charges can actually emanate electric field by themselves. So it means the direction of this electric field emanated by this positive charge will also be in the direction of the force. And that makes sense, yes. When we have positive charge, the direction of the electric force that will be experienced will be the same as the direction of the electric field. Remember, electric field for the positive charge emanates out of the charge. However, negative, it terminates into the charge. Perfect. So remember, the goal is to determine the electric potential energy. All what we are doing right now is a process that will help us to get to where we are going. Remember, we want to determine the work done in moving this charge from point A to point B. How can we determine that? That's our next question. Since work is equal to force times distance, since we are dealing with charge, the force will be an electric force. So, which is what we have already. Well, what about D? How can we determine D? D will be the displacement between A and B, or the distance between A and B. However, can that be determined? What do you think? Pause the video and see if it is determinable. Well, for it to be determined, we must have the distance between point A and point B, point B and the horizontal plate. Likewise, we must have the distance between point A and the horizontal plate. So let point A, the distance between the point A and the horizontal plate, let it be y1, and let the distance between point B and the horizontal plate, let it be y2. Now, how do you think we can actually get the distance between A and B? Well, notice that the difference between y1 and y2 would actually give us D, because taking B out of this y1, we would end up having this distance. Am I communicating? Perfect. So it means D is y1 minus y2. Now remember, work is force times distance. So therefore, we now have work to be equal to the force multiplied by. Now instead of D, let's substitute this value. Very, very important. So therefore, we have y1 minus y2. Now, back to relative field. If you recall, relative field is the ratio of force per unit charge, or the ratio of force to the magnitude of the charge, which means uppercase E is equal to the relative force divided by the magnitude of the quantity of that unit charge. And so therefore, upon solving for F, we would have F to be equals to EQ. So what we want to do at this point is, instead of F right here, we want to replace with EQ. So therefore, we now have the work done to be equal to EQ and multiply by y1 minus y2. Perfect. Okay, we are progressing. Now, this same work that we said is equal to force times distance, there's a theorem which we called the work kinetic theorem. This theorem says that the change in kinetic energy of an object is simply the work done. So you might be wondering, what does this mean? Let me give you a real life illustration. Consider a car that is moving at a certain speed. Then if the driver now decided to increase the speed, kinetic energy in this motion is the energy accumulated by the movement of an object, which means as you move more higher, as you move more faster, you have high kinetic energy. Am I communicating? Perfect. So for the driver to change its speed initially to a high speed, then it has accumulated high kinetic energy, or more kinetic energy compared to what he has initially before increasing the speed. Am I communicating? So this change in the kinetic energy is said to be a work done. Or let me disclose it in a more brilliant way. For this driver to actually increase the speed, he or she must have pressed down the accelerator or the throttle, whichever the case might be. Which pressing down the accelerator or the throttle is a force. Now, the way he or she presses down the accelerator or the throttle, the car tends to move in a more long distance. So now we have force and distance. Am I together? We now have force and distance. Now this clearly shows that we already have all the conditions that have to be satisfied in order for the work to be done. Am I communicating? Which means the product of that force, if we measure that force and the distance along which the object moves within the range at which the force is applied, then we will get the work that is done. Are we there? So therefore, the change, that's what that theorem is telling us, that the change in kinetic energy is simply equal to the work done. So W equal to change in kinetic energy. Perfect. Now, back to conservation law of energy. And now, let's pay attention to conservation law of mechanical energy. This law says that in an isolated system, energy can change from potential to kinetic. However, the total energy in that system is unchanged. Now, when we interpret this conservation law, it's of the form: the potential energy initially in the system plus the kinetic energy in the system initially. That is the total energy, at a certain point. it must be equal to the potential energy maybe at another point or finally plus the kinetic energy at another point finally. That's what that law tells us, that okay, the total energy in that system must be the same. So as we are changing position, so far we are the system is concerned, the total energy we must be having must be the same, which clearly means that in fact PE3 plus KE3 will still be equal to PE1 plus KE1. Am I communicating? Perfect. Now we want to use this equation. We want to solve for the change in kinetic energy. However, change in kinetic energy means what? KE2 minus KE1. So therefore, let's solve for KE2. So basically, I will take this right here. Then I will bring this right here. And so therefore, we will have PE1 minus PE2 to be equals to KE2 then minus KE1. So that is the change in kinetic energy. Now, instead of having it as KE2 minus KE1, let's put the change symbol. And so therefore, we now have, now I need to get rid of this at this point. Okay, let me just put this somewhere around it. So therefore, we now have PE1 minus PE2 to be equal to change in kinetic energy. Now, let's try to make this in a much more brilliant way. We can factor out negative sign and have change in kinetic energy to be equal to negative PE2 minus PE1. This makes sense. Now you can see PE2 minus PE1 simply refers to the change in potential energy. Now remember, we said that work done over here is equal to change in kinetic energy. It means instead of having change in kinetic energy, we can have work done. Are we there? Also, instead of having PE2 minus PE1, we can have change in potential energy. And so therefore, we can clearly say that the work done, which is equal to change in kinetic energy, is also equal to negative change in potential energy. This is one of a great formula you have to be familiar with while dealing with problems involving work done. So this is the same as negative change in potential energy. Perfect. Are we there? And that's exactly what we want to make use of. Okay, so now work done that is equal to EQ y minus y2. So it's the same thing as negative, because don't forget we are finding potential energy, negative PE2 minus PE1. Perfect. So now let's bring this negative right here. So we can solve for PE2 and PE1. And now we have negative EQ times y1 minus y2 to be equal to PE2 minus PE1. Perfect. So upon expanding, we have negative EQ y1, then minus EQ times minus y2. We have positive EQ y2 to now be equals to PE2 minus PE1. So now for this statement to be true, it means we can compare each side, the corresponding sides. Otherwise, it will not be true. But the fact that we have equal sign to be connecting them, then we can always do that mathematically. So it means negative EQ y1 is the same as PE1. Also, positive EQ y2 is the same as PE2. So now, okay, this is negative PE1. And I can see the negative can cancel out for at the left hand side here. Then finally, we can have the work done. Okay, so that is entirely. So it means the work done, which is equal to, we can have EQYI to be equals to 1 root I. EQY1 equals to PE1, okay, and then EQY2 equals to PE2. Excellent. So it means To get the electric potential energy at point A of this positive charge, all we need is Y1. Am I communicating? Y1, the magnitude of the charge, and the electric field intensity, which is the magnitude of the electric field. Then all we need is to multiply them. We will have the potential energy of the charge at point A. Same thing applies to point B. Once we have Y2, we'll be able to get whatever it is. And that's how to easily determine the potential energy of a charge at a certain point relative to the distance between that point and the horizontal plate or the horizontal guard. I hope you find this helpful and understandable. For easy understanding now to make use of this formula in solving problems, let's consider an example. A positive 30 microcoulomb point charge moves from point A to a point B, as shown in the diagram below. If the electric field intensity is 5.0 times 10 to the power of negative 4 Newton per coulombs, and point A and B are 40 centimeter and 15 centimeter above the negative charge plate respectively. Option A, calculate the potential energy at point A and point B. So first, let's write out what we know in order to find what we don't know. We are given the distance, or let's start with the charge. The magnitude of the charge Q is given as positive 30 microcoulombs. So we have to have it in coulombs. All we need is to multiply it with 10 to the power of negative 6. And therefore we have 3 times 10 to the power of negative 5. Excellent. Now we have the magnitude of the electric field E, that's given as 5.0 times 10 to the power of negative 4 Newton per coulombs. So that's in the appropriate SI units. Now, remember, we need Y1 and Y2, where Y1 is the distance between the first point or the longest point and the horizontal plate, while the Y2 is the distance between the other point that is closer to the horizontal plane. So, do you know how to interpret the statements? 40 centimeter and 15 centimeter above the negative charge plate respectively. What this means is that, we have point A and B. So what comes after that? 40 centimeter and 15 centimeter. So therefore, it is 40 that owns, it's A that owns the 40 and it's B that owns the 15. It's very important so that you won't be selecting the wrong value for the wrong parameter. So Y1 is 40 centimeter, which we have to have in meter. Y2 is 15 centimeter, which you also have to have it in meter. 40 centimeter to meter is 0.4 when you divide it by 100. Then 15 centimeter to meter, when you divide by 100, you should have 0.15 meter. Perfect. Now we have everything we need to determine the electric potential energy at each of these points. So let's find for A first. So I will represent that with PE sub A. P sub A is equal to EQ times YA, which is the same thing as Y1. And E is what? 5.0 times 10 to the power of negative 4. And Q is 3 times 10 to the power of negative 5. And we have the distance with 0.4. Then also PEB is equal to same thing, but times YB. YB is the same thing as Y2, and we have 5.0 times 10 to the power of negative 4 times 3 times 10 to the power of negative 5. Then just times 0.15. I will grab that, okay, because these two values are actually the same. So I will use my calculator for that before we get our final answer. So the first one, we have 5.0 times 10 to the power of negative 4, then multiply by 3 times 10 raised to the power of negative 5, and finally multiply by 0.4. So I got 6 times 10 to the power of negative 9. Wow. So it means for PEA, we have 6 times 10 to the power of negative 9. So what about PEB? So for PEB, instead of, I'll just get rid of 0.4 and put 0.15. Then I got 2.25. 2.25 times 10 to the power of negative 9. Same index, relative to 10. So this is the electric potential energy at point A and point B. That gives us the answer to part A. On to part B. What is the work done in moving the charge from point A to point B? We discussed it while explaining everything you need to know about electric potential energy. So I'll use that as an exercise for you. Let me know in the comment section below. What is your answer? Thanks for watching once again. See you in the next video. Bye for now. By the way, if you are yet to subscribe, feel free to subscribe. Thank you. Bye-bye.